Okay, let's get started. I understand this is the last session in this room today. I'm sure many of you are exhausted after day one of Reinforce. Thanks for coming to learn about a very simple and easy to understand topic, which is how do you get assurances that unauthorized users don't access your data in the cloud? So, for those of you who have seen some other encryption-related presentations today, this will try to focus a little bit more on how you prove things to yourself, how we prove things to ourselves, how you can get some evidence that allows you to prove things to others inside your company, whether they be regulators, auditors, or people inside your IT security group. So we'll start at a high level. Why encrypt in the first place? And these are common reasons we hear from our customers. We think that it boils down to minimizing unauthorized access to data. Now, I'm separating physical access from logical access because physical access is easy for people to understand, right? I can hug my server, I can stick a USB token or a serial cable inside a device or port inside my server and somehow get data directly off of it. But of course, physical security is not something you even get to worry about when you go to the cloud. And so logical security tends to be the thing that's more relevant, but it's also a little more abstract. So let's talk about the ways that you might minimize unauthorized physical access to data in the cloud. So if you are transporting your data to the cloud over the public internet, maybe it's a dedicated direct connect, you still are thinking about what are the possibilities for man-in-the-middle attacks, any type of sniffers that might be in between you and the connection there. All right, that's one of the reasons why a lot of people tend to use Direct Connect or look at encryption mechanisms for transporting data on the wire. Of course, if you're moving very large amounts of data via snowmobile or even individual snowball devices, now you have to ensure that what happens with compromise of that data as it moves from point A to point B. Now, data at rest, in this case, you want to be thinking about who are all the people that get inside AWS data centers, right? What do they have access to? What's to stop an AWS employee from pulling a disk and going home with it? All right, again, these are things that you can't easily reason about because we don't let you into our data centers, right? We let our auditors into our data centers, but you don't get to do this. And data in use, so if you assume that your data is actively being worked on by some compute process, it's inside memory, inside a physical host, then how would you know whether or not people have the ability to take a device that is actually processing data in memory and do something to it to be able to retrieve that data? So with logical access, some of the same controls come into play when you're talking about data in transport or data in transit, right? Network access controls become very critical. We don't give you the opportunity to think much about layers 1, 2, and 3, but layer 4 access controls and then application layer access controls are something we do give you some controls over. So data at rest. And this is a big part of putting your data inside a cloud service because you get at least in the case of AWS, a thing called an Amazon resource name, an ARN. This represents your EBS snapshot or your Redshift cluster ID. And now you have to build logical controls to ensure who has the ability to cause that data to be transported into memory on a live instance and therefore accessible to anybody who has access to the instance. Encryption is a good mechanism as a belt and suspenders approach to say, while this data is at rest, until I declare that I want it to be active and accessible, I want it to be scrambled so that if anybody does have the ability to pull a disk and take it away, that they won't be able to decrypt it. Data in use. So this is where we think about an EC2 instance where the compute resource and the memory resource belongs to you. Now, do you have controls to ensure that unauthorized users are not able to get into that instance? Perhaps sudo into your Linux shell, or power users that are getting into your Windows environment. That's a control that you are responsible for. But you also want to think about, again, what are the ways in which humans working inside data centers might be able to get access to your data that's running inside EC2, or your data that's being pushed to a managed service. So when you transfer data to S3, it goes through a web server that receives your put request. What do we know about the security controls on those servers to be able to prevent humans from accessing that data? So let's talk a little bit about the persona involved here. So I'll show three here. The software developer who is eager to go build great things. And they've been given thousands of APIs from AWS to go stand up resources and transfer data from your business to go build cool applications. So the keys that are being used, and there's typically two types of keys, authentication or access keys, and then encryption keys. And this developer wants to do the right thing. And of course, they want to be able to do the right thing easily, and they want to do it at scale. Then there's the IT security group that is perhaps fundamentally responsible for the confidentiality and integrity of this data. They have policies and processes that they've been using for on-premises systems for years, and they want to map those to the developer who's trying to move the workload to the cloud. So how does this person think about minimizing physical and logical access to data? And then finally, there's a role of somebody in compliance, whether it's internal or external. And they're effectively looking for evidence that the developer did the right thing when the data was moved from point A to point B, and IT security is doing the right thing to monitor all the developers, and there's evidence that the proper security and the proper controls have been put in place to minimize unauthorized access. So we'll talk about various features as well as documents and ideas that we have to share about AWS security in the context of these three people. So in the context of encryption, for years, I've gotten the fundamental requirement that says, well, we'll move to the cloud, but only if we control all the keys. Now, the question is, well, Mr. Customer, what do you mean by control all the keys? So from taking the word control, we think that you actually do need to put very stringent controls on the access keys that you use. Because the access keys, whether it's in the form of API signing keys or a password that you use to log into the console, this is what uniquely identifies you as the individual developer or as a role, a group of people that are attempting to cause an AWS API to do something for you, right? And if you do not keep the secret access keys or the console passwords private, then anybody can impersonate you. So this part of physical security of credentials is actually your responsibility, which is why we recommend that for highly privileged accounts or users within those accounts that you MFA protect those credentials, and you take the MFA device and you put it in a safe somewhere, or you get some type of separation of control to ensure that it's hard for an attacker to impersonate you and cause things to be happening inside AWS. And of course, the ability to modify any policies or permissions that apply to those identities is a critically important role. And those users and their credentials need extra security. Now, the compliance person is going to be interested in knowing, well, what changes were made, right? Alice was a privileged administrator with IAM star.star permissions, and Bob all of a sudden got those same permissions. Was that an authorized escalation of privilege for Bob? Right? When did it happen? Against which resources or which accounts does Bob now have IAM star.star permissions? So completing the cycle from defining your access policies at least defining the mental model, as well as writing them down and acting them using policies inside AWS, whether it's the console or programmatically via JSON files, and then looking at things like CloudTrail to say, okay, this API action was called, put policy was called, it made a change for a particular user. That closes the gap for the compliance team. Now, the nice thing about access keys is that they can be rotated at any point, and you can forget old keys, right? And that's a best practice. In fact, we strongly recommend that you take advantage of temporary security credentials and access keys wherever you can via the roles for EC2 feature, where we rotate new creds every hour and push them to the instance metadata service on EC2. However, with encryption keys, while you can rotate them, you can't get rid of old ones. Anything that's been encrypted under a given key, if that key is leaked to the wrong folks, they could potentially decrypt that piece of data. So here, we're actually concerned about durability of keys, and those keys have to be very close to the data that they are encrypting. And we recommend that you allow your cloud provider to store keys as close as possible to your workloads so that they can be used and minimize latency on any reads and writes that you need to do. So now you have to worry about, well, is my cloud provider going to keep these keys durable? Or do I need to worry about them losing a key that might be ultimately responsible in a hierarchy to protect billions of S3 objects? Again, like permissions on users and roles, you want to be able to define permissions on keys. And those need to be independent permissions from the access to the resource itself. So an S3 bucket policy that says Bob and Alice have get permissions to pull objects from that S3 bucket. But there's certain data inside that bucket that's encrypted, and only Alice has permission. So she only gets permission to call decrypt against the master key required to encrypt that object in the S3 bucket, which means Bob, while he can, quote, get the object from an S3 standpoint, doesn't get any data returned because it can't be decrypted. Right? So managing those different policies and having an audit every time a change was made to the key policy to access encryption keys is just as important as being able to have those types of controls on your IAM policies. So Steve Schmidt showed this slide this morning, trying to give you a sense of the OSI, maybe not all 7 layers, but many of them, to explain where cryptography is being used. So what I want to focus on here is that as you, at least in this diagram, go down, but actually go up in terms of layers, more towards layer 4, layer 7, we're starting to give our customers more control over whether or not things are encrypted and the keys that are used to encrypt those channels, whether it's data in transit or at the application layer to also include data at rest. Now, the lower level for physical layer, data link, those are, if you imagine, default encryption, right? And we're actually using different technologies than we provide at the higher levels. And that's a best practice because you don't necessarily want the exact same algorithms used to encrypt packets of data going across the network. If those packets are going to be encrypted at rest, use a slightly different algorithm. Okay? This again provides multiple levels of protection so that if there were to be a breakdown in any one of those levels, or if you made a policy mistake in giving somebody access to decryption keys that shouldn't have that access, you get some protection at the other layer. So let's start with talking about data in transit security. So what's available today? So VPC encryption that will transparently encrypt connections between EC2 instances across a VPC. This is available in the newer instance types that take advantage of the Nitro hardware. Then there's 3 different flavors of VPN. So from your data center to the AWS cloud, you can make encrypted connections using some of our managed services, whether you're using Direct Connect or not. And then, of course, you can always install your own VPN terminator inside an EC2 instance and use that, along with IPsec, to encrypt data that's going into the cloud. So we're not done innovating in this space, because we think that there are valid reasons for you to have encryption on every single connection. Anywhere where there's point-to-point data going between logical instances or physical devices on your data center, between AZs, between regions, we want to make sure that there is at least a strong and sane level of default encryption. And over time, we're looking at ways in which we can give you control over roots of trust for that transport security. Okay, if we go up a little higher above where IPsec plays into layer 7, so TLS over HTTP. Right? If you are terminating a connection from one of your customers, one of your internal users, you have options there. You can have that termination handled inside your own web server instance running on EC2, inside ELB, including the network load balancer and application load balancer. You might be using the content delivery network CloudFront to be able to terminate stuff that you're trying to make available for your websites. And finally, API gateway. So in each of these cases, you're able to bring your own digital certificates, your own digital cryptographic identity. If you get your certificates from an existing CA, then you can insert them into these endpoints and use them to terminate TLS. Okay? But what if you don't want to be managing certificates? If you don't want to acquire them, whether they're either too expensive or it's too painful to acquire them, transport them securely, and then deploy them to the right endpoint. So we introduced Amazon Certificate Manager a couple years ago. And in the context of public certificates, so these are certificates where the root of trust is likely to be inside the common trust stores available in browsers as well as SDKs. So again, in this model, we generate the public and private key pair. We create the certificate using the distinguished name information that you give us that you want for your domain. And we can automatically provision this down to your TLS termination endpoints. ACM handles the painful parts of managing a PKI, right? Strong entropy sources to generate key pairs, the certificate signing request, taking the private keys and making sure that they themselves are protected in storage, so you get durability of your certificate and private key, but it's encrypted at rest. And finally, the big one, which is the managed renewal and deployment. So we can push the certificate down to the endpoint where it belongs, and ACM will know when it's time to renew in a year and automatically run through the process again to generate new key pairs or extend the life of existing keys in renewed certificates. Okay? And because it's a public CA here, we need to verify that you actually own the domain that's going to be inside the DN. And we can do this through both DNS validation and email. Private certificates, or private CA, is a slightly different spin here, where the root of trust is actually something you define, because the trust store on the client side that's trying to evaluate that root of trust, again, you control. So this is more internal components where you want encryption from point A to point B, but you don't necessarily care about the root of trust inside the certificate on the server side. So one of the nice things that we announced last week is the ability to have private CA generate certificates and then export them in encrypted form, and you can take them and move them around to different systems. So just like you could bring your own certificate to EC2 and install that inside a web server, you can now have private CA certs generated and exported and use them inside EC2. Another nice feature that we introduced was this idea of creating your own root. So it used to be you had to have an existing CA, and you would give us an intermediate cert and declare that to be an issuing intermediate cert. Now you can ask ACM to say, just create me a root. Here's the fully qualified domain name. And now I'm going to generate certs underneath that. So it gets even easier. Okay? And all of the good stuff that we can do with public certificates, we get to do this with private certificates. Now, if you are exporting certs and now taking that material and putting it in some endpoint that we don't necessarily control, whether it's an EC2 instance or some server outside of AWS, we still can do managed notifications. And we will automatically generate a new cert and have it available. So if you have a client that's frequently polling the service to say, hey, is there a new cert available for me to talk to this endpoint, that will be available for you. So let's dig a little bit deeper about how do we ensure that unauthorized users don't go in and somehow hijack certs and pretend to be your domain or your identity. So how does this process work? I'll use the example here for public certificates. So certificate manager gets a request, says, if I log in, I say, I want a public cert for www.kenbeer.com. Right? It'll go through DNS validation to make sure I actually own the domain. Then it will generate the RSA key pair and create the certificate in memory on one of its systems. Now, it has to be able to store that somewhere for durability, because the existence of the certificate is nice, but at some point in the future, you're going to want that deployed out to end devices. So before this certificate and the key material is actually written to disk, ACM calls out to the key management service and says, I need a data key. This is going to be a 256-bit data key, and it is going to use that data key to encrypt the package of certificate plus private RSA key. So now this ciphertext blob sits in storage in ACM. At some point, you're going to say, all right, I'm ready to spin up another elastic load balancer if you happen to use that service. Elastic Load Balancer has a config that says, hey, I want to use this particular certificate that is available in ACM. So ELB will then call to ACM and say, give me that ciphertext blob that represents the certificate. So again, we're passing ciphertext between two systems, the ACM service and the host that has your ELB on it. Now, ELB can't use that encrypted blob for anything because it's encrypted. So what does it do? Well, it actually uses your identity when you spun up the ELB. You asked ELB to create an instance. And it passes the encrypted data key that ACM previously got, passes it to KMS under your identity, and says, please return the decrypted data key. So again here, the actual RSA private key and your certificate have not left the ELB memory on that host, right? Just the data key needed to decrypt it. And once it gets the data key, it then decrypts that blob and provisions your private key and the certificate into memory, so it can now terminate TLS, and your clients trust it. When that ELB goes down, either because it's our fault, or you say, nope, I want this ELB to stop or to terminate, then all the key material, including the private key, disappear. And we go through this dance for every single ELB, or every single CloudFront endpoint, or every single ALB or NLB. It goes through this dance to get the necessary decryption keys from KMS, again, using your user's identity. And that user has to have permissions to call KMS decrypt for that process to work. Okay? So the next question should be, well, that's great, Ken, but I can't see any of that happening. So how do we know that you guys are doing it correctly? Right? And this is where we invest heavily into third-party compliance schemes and getting audits of our own services and our own technology so that you can trust that things like, for example, when we issue the certificate and we create those keys, are we adhering to best practices that are expected by all public CAs on the planet? Well, yes, we do, because we get our Web Trust audit done every year. We're members of the CAB forum. For anybody out here in Europe, you know that Etsy has a standard that's very similar to WebTrust. And that's just for the certificate generation and storage. The entire service and all the security controls around software change control and privileged access by administrators all fall under our standard compliance schemes like the SOC or ISO 27000. In GovCloud, we operate ACM, and therefore it's ITAR compliant. Right? So the items on the left there are pretty standard across most services, and you'll see the security-focused services have a whole raft of these compliance schemes. And that's because we know that we've hidden a lot of the secret sauce around the generation and handling of sensitive materials, but we want you to make sure you can connect the dots, either with your own IT security team or with an external regulator. Okay? Something else that we let you do is where we're using open source, either for, say, key generation, encryption processes. In this case with S2N, this is the TLS protocol that we use in our own services. We give you the ability to download the open source, and S2N actually has, you'll see the fourth bullet point there, an automated formal verification process that ensures that the outputs of cryptographic operations as a part of a TLS session negotiation are correct for all potential inputs. It's kind of like an integration test that we do ourselves with the open source that we publish to GitHub. And we do these same tests every time we publish this code package to our own services API endpoints. Okay? So here's another opportunity for you to say, well, sure, at that point in time, Ken told me this stuff was secure, or the SOC audit that happens twice a year, yeah, and those 2 points in time during the year, maybe things looked good, but how do I know it's always running and always giving me the security properties that I want? Well, we think that giving you access to the code that we use and having you run your own tests on it is one way to help raise the bar there. Okay, so let me change gears and talk about data at rest security. So I'll go through this next slide quickly because I've done it almost every year, and hopefully people are aware of envelope encryption. But we use symmetric key encryption for block data encryption. Why? Because it's incredibly fast, and it's the most efficient way to do things. When you create ciphertext with a symmetric key, you get to put that ciphertext wherever you want. If you believe in the security properties of something that has been encrypted correctly with AES, especially using 256-bit keys. However, the plaintext symmetric key is now at risk. You can't lose it, but you can't store it on disk in plaintext, right? You can go put it on a USB stick and carry it around in your pocket, but you still have some durability concerns, not to mention some confidentiality concerns if anybody finds something in your back pocket. So what do? Well, we take this particular data key and we encrypt it. Under a key encrypting key, we use the term master key in this case. So now the encrypted symmetric key and the data can live side by side. And this actually has some nice durability properties because it's unlikely that you're going to lose the ciphertext that represents the keys, but still have the ciphertext of your thing, right? If one of them gets lost, they're likely both going to get lost. Okay? However, I've used a key to encrypt a data key, which was that red key. Now it becomes its own problem, right? And so we can keep encrypting all the way up the hierarchy ad infinitum. At some point, there has to be a plaintext symmetric key that's available to use to then unwind all the way down the key hierarchy, right? And the trick is, where do you keep those plaintext keys, right? And that's one of the reasons we invented the key management service as a place to keep the plaintext keys at the top of the hierarchy and ensure that only authorized users would be allowed to make use of those keys to then decrypt key hierarchies and all the keys down the chain. So that's what key management is about. That's why it's a particularly challenging problem at scale when you need copies of the plain text keys to be in lots of different locations so you minimize latency from your applications. So in AWS, we give you two different options for encrypting your data. Client-side encryption. So your process that generates your data, let's say it's an EC2 instance, is going to do encryption and then send it off of the instance to some storage service. So in this model, we supply some helper applications, which could make the process of encryption and decryption easier for you. Note that those helper applications themselves don't give us any particular access to your plain text keys. They're just SDKs. You actually have to choose your key provider. You may very well have one you like that you've been using that works inside your applications. If you don't, we give you access to one where you can take advantage of KMS. You configure a master key provider inside these SDKs. And the interface for the developer that's using this is pretty clean. The other option is server-side encryption. This is where you ask the service that receives your data, hey, please encrypt this before you actually write it to disk. And here, we are integrating key management service with 54 storage services today. So all of the primary storage services that you're familiar with all support KMS. And any new services that get developed that might take your input are going to encrypt that data. In fact, you heard Steve talk about this earlier this morning. 117 services will do some form of encryption. Sometimes it's transparent, where you don't get to see anything about the keys, and sometimes it gives you full control over the keys via KMS. Okay? So let me dig a little bit into how client-side encryption works, or what the options are. So if you start with data that's inside your data center, and the goal is I want to get it to one of the storage services in AWS. Now, if I want to encrypt it, I have to have some type of client application that's going to do encryption, and I have to have a source of keys. You may already have this on-premise, right? Customers have been doing this ever since AWS began, ever since S3 opened for business. People have been encrypting somehow, some way, and then sending S3 ciphertext. The other option is you might actually have your encryption technology and your key management systems running in EC2. Could be using a third-party solution, a partner solution from companies like Vormetric, which is now Thales eSecurity, or Udemako, or SafeNet. There's lots of partners out there with encryption and key management solutions, many of which might be similar to what you've been using on-premise. Okay, so at the end of this, you get your ciphertext and you give it to the AWS service to store, and that service doesn't know anything about how to decrypt it. It has to come back through your client application for it to be decrypted. So the alternative is that your client application gets keys from an AWS service, either through KMS using things like our encryption SDK, or you can connect to our Cloud HSM service, which supports a lot of the classic cryptographic protocols, PKCS11, JCE, CNG. The end result is the same. The storage service is going to get ciphertext it knows nothing about. Okay? So the SDK, the goal here is that as a developer, I just have to keep track of where my plaintext is and what is the master key provider. In many cases, what we see customers doing is they will take the SDK, they will configure it with a master key provider that either works with their internal KMS or something like AWS KMS or Cloud HSM and say, here, developers, here is the package you should be using. And there is exactly one method. It's called encrypt. And out comes ciphertext. Developers don't have to think about which mode of AES, what length of key, how long does the IV need to be again? Oh yeah, and where's my entropy sort? Like, those are questions that if you force a developer to try and answer, more likely than not, they're going to make the wrong choice, simply out of ignorance. So, easy to use, some interesting use cases. In fact, we've had some presentations earlier today from my team about how to be able to use this SDK to encrypt data at the time of write using keys from different regions. So if you have a DR story where you want to replicate encrypted data between regions and make sure it's always readable in the destination region, you can do that with the encryption SDK at time of write to make sure that something is encrypted with multiple keys from multiple regions. Another nice feature of the SDK is that we give you some mechanisms to cache or reuse data keys. So if you're doing some type of streaming or very high throughput, high request rate applications where each individual file, in the classic sense, you might say, well, I want every single object to have its own 256-bit key. Therefore, I'm going to minimize blast radius in case one of those data keys happens to go walking. Well, if all of the data that you're encrypting is a part of a single data classification, maybe West Coast customers or PII or whatever the data classification is, from a security standpoint, it's actually okay to reuse a data key several times. In fact, AES in Galois counter mode can be used up to 2 to the 32 times before you end up in a state where you have a probability risk of collisions in terms of IVs and or ciphertexts. So how do you do that? How do you manage the reuse of keys? Well, you've got to make some decisions based on time, based on the number of operations, based on the number of bytes that you encrypt, and the encryption SDK gives you those choices. The encryption SDK available in C, Java, Python, and of course, the AWS CLI. So we recommend that you take a look at this so that if you have to build secure applications and you are trying to help your development team, they should be pretty excited about this. Feedback over the past couple years has been, hey, this is interesting and can be used whether or not you're using an AWS cryptographic service. Okay, now let's talk about server-side encryption. So the model here is classic envelope encryption. If you look at the bottom there on the right, a given service like an S3 or an RDS or an EBS is going to get a unique data key for a given object or a given resource. That data key is then encrypted under a customer master key or a CMK inside KMS. When you instruct EBS to create an encrypted volume, you pass in the KMS CMK ID inside the create volume API call. Okay? And we do this envelope encryption because we think that it's easier for you to manage a relatively small number of CMKs that map to various data classifications, as opposed to getting a referrer ID for every single one of the data keys that might be used for billions of objects inside S3 buckets, right? Or tens of thousands of EC2 instances. So now on the KMS side, let me dig in a little bit here, because if you're thinking about, well, how do I prevent unauthorized access to my data if that CMK, that master key, is actually protecting, again, billions of data keys for S3, then maybe I'm better off attacking KMS as opposed to going to dig around inside S3 just to find different data keys for every single object. So let's talk about how the protocol, if you will, works when services or your own clients call KMS. So if we start with data that needs to be encrypted, you've got some client application, whether you're using our encryption SDK or not, or an AWS service that's acting as a client to call KMS. So we have an API endpoint, just like every other service. Connect over HTTPS. As it turns out, the TLS cipher suites that we support, we mandate that you use ones that support forward secrecy. So things like elliptic curve, Diffie-Hellman, ephemeral. Right? Because this is a best practice. We don't want people capturing your sessions to a KMS API endpoint, storing them, and then coming back down the road when they somehow have an ability to crack keys and being able to replay those sessions. So the API endpoint terminates TLS also does the authentication and authorization. Says, is this principal that's inside the API signature allowed to do the thing inside KMS, whether it's getting a new data key, decrypting, modifying the state on an existing CMK, any of the 44 or 45 KMS APIs always get authenticated and authorized. And then, of course, if it's whether it's an access denied or an actual successful API call, there's going to be a log that's written to CloudTrail. And this is true for every single API call. So if you are authorized and you need some cryptographic operation done, let's say it's a decrypt, then your payload, which at this point is a piece of ciphertext, gets passed back to the KMS HSMs. So this is a fleet of stateless HSMs, and their job is to simply take a bunch of ciphertexts that we give it and use the keys, the plain text keys that it has in memory, to start unwrapping things down through the hierarchy until it gets to the thing that you want decrypted. And then it connects back to our API endpoint, which then returns a decrypted thing to you. That decrypted thing could be a data key, as it turns out, if you're doing your client-side encryption, or it could be an actual small piece of data, anything up to 4K. Okay? So all the cryptography happens inside these HSMs. Now, we can generate those master keys for you, or you can import those keys from your existing on-premises systems. Right? One of the things about when we generate the key, we make sure that we keep tons and tons of copies of that key in encrypted form in multiple locations, independent storage services. Those keys are the most durable objects that AWS manages for customers. But you might say, that's nice, but losing a master key is pretty catastrophic, so I want a copy. Well, if you generate your own key, you can actually import it into KMS, and you're going to transport it by encrypting it. You're not going to rely solely on TLS. And once that key is inside the service, it can now be used just like any other CMK, even if we generate it ourselves. Last year at reInvent, we introduced a feature called Custom Key Store, where the cryptographic operations actually happen in cloud HSMs. So if you have a cloud HSM cluster, then all of the key generation, encrypt, and decrypt operations will happen inside those devices. So if your regulations or your IT security team says, we want HSMs we have more direct control over, we want to be able to act as the crypto officer, we want to be able to create a session directly with these devices and do some type of signature verification on the identity of these devices. Right, a lot more operational requirements for Cloud HSM, but may very well fit your needs. We invite you to do that, but still use the KMS API set as the front door, right? As well as the ability for KMS to integrate with those 54 services. So yeah, the crypto is happening inside your custom key store, but the interface to it is very AWS-like. Okay? So now let's drill a little deeper. In the case where we are generating the master keys for you, even the data keys, the key hierarchy basically looks like this. Data keys, you can call the generate data key API. We will return to you 256-bit data key, as well as an encrypted copy that's encrypted under the master key that you designate. Then there's a CMK, or the customer managed key. The customer master key. It's the master key that encrypts data keys. That key is always 256 bits. Any operations performed under that key are always AES GCM. And anytime the key material is in plain text, it's only in the memory of one of our HSMs. It's the only place it can exist. How do we ensure that? Because CMKs are encrypted by keys higher in the hierarchy, and those keys are actually generated inside the HSMs at time of provision and only ever exist in memory. So you can see we can give you durability on CMKs, And services that use data keys to protect your data will give you durability on data keys. But the keys at the very top of the hierarchy, it's one per HSM. And if that HSM dies, that key is gone, which is why we have lots and lots and lots of them. So we actually don't care which HSM the operation gets sent to, because we know we can decrypt it by working down the hierarchy. Now, you might scratch your head and say, well, wait a second, how does that work when you've got thousands of HSMs? I invite you to look at the Cryptographic Details white paper that we publish to learn a little bit more about this concept of HSM domain and how we build a domain trust inside a given AWS region. So the CMKs and the keys above them are all stored by KMS. Okay? So the access control mechanisms we have on our HSMs and the claims that we make about that, that's where you start to convince your crypto team, your PKI team, your HSM team, your regulators that the way we've built KMS is sufficient to meet requirements for how you manage master keys. Okay? How can that be true? Well, some useful things to know about how we operate the service. When we provision an HSM, we actually turn off all the interfaces. So all that's left is an API. And then there is no API that says, get me a customer's master key, or get me one of those root keys that's in plain text in memory. There's also no way to push software to the device once it's provisioned. So we have an understanding of the state of the software and the firmware. And one of the things that we've done with our FIPS validation is that we actually have version numbers for these HSMs, and you can look at the security policy on the NIST website and know that version 1.4.3 or 1.4.4 is running in a given region, and it doesn't change. Because when they're operational, they can't be changed. Okay, well, what if we want to upgrade the firmware, right? Or if there's some kind of emergent bug that we need to fix on your behalf. First, we have to shut down the device. We wipe all the memory, so there are no keys left on it. And then a different API opens up, and we're able to push new firmware or software to the device. However, the life cycle of that code is such that it has to be reviewed by multiple employees on the team, not the person who wrote the code. It has to pass integration tests that ensure that the state change from plain text keys to encrypted keys is still consistent with the previous version. All right, so this is part of the formal verification that we've done as a part of the automated reasoning group at AWS. And we've put that into our build cycle so that if our developers are trying to innovate quickly in a particular area of code, they can't change the fundamental security properties of the system. The build just fails, right? And then they get to go back to the drawing board to figure out how am I going to do this innovation, but still pass this particular integration test. And finally, once we have an image that we believe has whatever new functionality we want or bug fixes and maintains the security properties, those images can only be deployed into prod if 2 authorized engineers perform a digital signature and push it through to prod. Okay, so what we're trying to do is minimize the risk that one engineer who has access either to source code, the deployment pipeline, to the prod network, can one engineer do something to change the security properties of the service? We assert that the answer is no. It would take multiple failures, multiple coordinated failures across multiple people to change the security properties of the service. Okay? That's why we put a control inside our SOC report that says that no single employee can gain access to the key material. Now, there's a lot of tests that happen as a part of our SOC audit. They're looking at 4 or 5 different ways in which people might access the build system, the prod network, so on and so forth. But this is the language of our SOC control. And I want you guys to be thinking about the SOC as a way for you to get some of the verification and attestation in the language that you need to convince your customers, regulators, so on and so forth, that AWS is doing what it claims to be doing all the time. We get to invent claims in the SOC and then have third-party auditors hold us accountable. We'd love to hear some more claims that would help you trust AWS for some of your more sensitive workloads. Okay, so now let's pop out again into the gory details. Let's talk about what you get to control with regards to the use of encryption keys. Well, you get to control a thing called a key policy, which in a general term is a resource policy, kind of like an S3 bucket policy or a SQS queue policy, right? These policies are written in JSON the same way that all policies and permissions in AWS are written. And that key policy is the first thing that we look at as a service to determine whether the principal that's trying to make the API request is allowed to do the thing they want to do. Okay? So these are examples of controlling different API actions. Encrypt and decrypt are the interesting ones, but also things like creating keys, disabling keys, scheduling keys for deletion. Very powerful APIs that you want to make sure you've got only the right sets of people able to perform those actions. And all of this is fully integrated with the IAM policy language and systems that you're used to using across the rest of AWS. So let me talk a little bit about how a target service would then use data keys. So we explained how envelope encryption works, and hopefully you understand that the master keys are strongly protected, and you have some sense of, yeah, there's not going to be unauthorized access to plain text master keys because of the way it's built and the SOC controls that it has, the FIPS validation, so on and so forth. But when a data key goes to, let's say, the EC2 server to encrypt all of your traffic from your instance down to your EBS volume, what about that system? Right? What do I know about that and the security of those keys? So there's two general models for how AWS services use data keys. The first one we've just called the EC2 EBS model because it was the first one. There's probably a better name for it. But the idea here is that every resource that is created gets its own data key, but that data key has to be provisioned in memory for the life of that resource. So if you think about EC2 instances or RDS databases or Redshift clusters, there's a life cycle where you say, create this thing, make it available to me, and at some point you're then going to say, okay, stop this thing or terminate this thing. So those verbs should be familiar to you if you use EC2 APIs. So as long as an EC2 instance is up and available, it has to be able to accept any I/O that you give it and write that data to disk. And if you're using a system that expects 5, 6, 10,000 provisioned IOPS, you know that you're not going to make a network call back and forth to KMS for every single one of those reads and writes. So a data key has got to persist somewhere in the chain from your instance down to the EBS volume. The other model we've called the S3 model, which is, okay, we need a data key, but only for a short period of time. We just need to encrypt something, and then that thing is going to get moved on to another system. So if you think about S3, when you make a put request via the API, it is going to encrypt your data inside the web server, and then it's going to send it back into its own storage node and shard it up into at least 3 different parts and do all the wonderful things S3 does to give you 11 nines of durability. So there your data key only exists in memory for very small periods of time. Okay, so let's dig a little bit deeper on EBS encryption and understand, all right, how do we know these data keys are safe? And how do we know that unauthorized users aren't going to steal data keys that they could use then decrypt my RDS databases or my sensitive AMIs? So Alice wants to create an EBS volume on which she's going to put data, or maybe this is a part of an AMI that she's creating. First thing that happens during that create volume call is she passes the ID of a KMS CMK. EBS will call KMS and say, hi, I'm calling on behalf of Alice, and I actually am making this rather long API call with a long name, generate data key without plain text. Okay, I'll explain why it's without plain text in a second. So what happens is KMS says, OK, is Alice allowed to make this call? We're going to check the key policy of the key that she wants to use, the master key. And we're going to go to the IM system and find out if there's any other policies and determine whether Alice is authorized to make this call. If so, we're going to deliver an encrypted data key. So it's a unique data key, and it will be assigned to that EBS volume. But the data key is not in plain text. There's no data written on the volume. Things are in waiting. At some point in the future, which could be seconds, but it also could be months, Alice will say, OK, I want to attach this volume to an instance and start writing data to it. So at this point, there has to be some plain text key that's provisioned so that all writes can be encrypted to the volume and all reads can be decrypted. So what happens here? Now EC2 will make a call to KMS and say, hi, it's Alice again. I have this encrypted data key, and I need to be able to decrypt it. So does Alice have permission to call the decrypt API for KMS? Because I need to get that plain text data key out of the ciphertext that you created for her some period of time ago. If so, one of the things that happens in the new instances, so the kind of the C5 family and above that uses the Nitro architecture, KMS actually doesn't decrypt this data key and send back plain text. Instead, it actually re-encrypts that data key under a public key that the EC2 instance provides to KMS. Okay, this is a little complex, but the idea here is that it says, OK, KMS, inside your HSMs, decrypt the data key, so you get a plain text data key, but re-encrypt it with this public RSA key that I've given you. So that, again, ciphertext is being pushed from the KMS service all the way down to the EC2 instance. You're not relying on TLS for all of your confidentiality and integrity, and you don't have to worry about all of the hops and all the switches that might be between the KMS service and the EC2 system. So now the question is, well, how does EC2 decrypt this thing? Well, they've got the matching private key, because these are uniquely generated as a part of you spinning up every instance. So now it provisions the plain text data key inside the Nitro card and uses that to encrypt and decrypt all I/O. OK, so where does it store that key? And where was that private key that we talked about? Well, that's inside the Nitro security chip. So if you haven't heard a detailed description of the Nitro architecture and how we've built it so that there is no way for humans to access data inside the Nitro infrastructure, I recommend you chase that down. It's very interesting. The idea, again, these Nitro cards are kind of like little mini key generation systems. They will generate private and public key pairs for themselves that are unique to the identity of an instance, and we'll use those to be able to encrypt and decrypt data as a way to pass it back and forth. And that's how they get the KMS data key. So we've gone deep, we've come up again. We haven't talked much about the compliance officer. How do we make that person happy? Well, every single call to KMS, whether it was a part of that EBS encryption dance or part of S3 or your own client doing things, is going to show up inside CloudTrail. So here's an example of what might appear as a part of Alice trying to get that EC2 instance launched and an EBS volume attached to it. Evidence of a decrypt at a particular time under the unique ID for the customer master key. And you'll notice this encryption context, which is the ID of the volume that she created in the first step. Every volume gets its own unique ID. That information is passed into the KMS calls so that when you look at the KMS logs in CloudTrail, you can say, oh, yeah, that's right. At that time, we did ask that a volume get created and get attached. Right? The call came from a particular IP address, and here's the identity. In this case, user 123 would map to Alice. So you can complete the circle. And we have customers that will do analysis on CloudTrail events and look for anomalous decrypt calls. Or if it's a decrypt call, let me look at the encryption context. Is this a resource I own? Is this a resource in my account? Did I actually want this resource decrypted at this time? Okay? So, again, there's a lot of, maybe slightly more than hand waving, but you got to believe some of the things that I've told you about how things work because you can't see it for yourself. So we look for third-party compliance schemes like FIPS 140-2 to prove that the cryptographic modules inside our HSMs are operating correctly, and we don't have ways for keys to go walking off of these boxes. We also rely on the SOC 1, 2, and 3 as a summary report, where we invent our own controls to try and give you insight into how we operate some of our secure services, and the security controls are always in place. And then, of course, loads of other compliance schemes, many of which are unique to different geographic regions, that speak to the general operation of a service, just like any other AWS service. So for those of you who have to deal with compliance auditors, you know it can be painful. Sometimes you have to change your application design and change evidence. When we built the KMS team and some of the other security services, we said if there's a compliance scheme out there that talks about data privacy, we want in. So we have a dedicated team that focuses on providing evidence. And we have our own checks and balances to ensure that we're always meeting all the requirements as a part of these things. Because we know that since you're never going to touch the hardware or the software, you have to rely on some type of third-party testimonial. Okay, so for those of you who have QR readers, you can do this now or when this gets posted to YouTube. There's some other resources that I think are useful. I mentioned the Cryptographic Details white paper. So this is approximately, what's it up to, about 40, 50 pages that goes into detail about how we built these stateless HSMs, how we can get to 1,000 HSMs inside a single region and still ensure that the confidentiality and integrity of your keys is intact. We have a best practices white paper that focuses more on how do you think about in which accounts to create your keys, how do you delegate access across account. Given that these master encryption keys are pretty sensitive pieces of information, we think it's useful to centralize the creation in a single account and then delegate out to other accounts so that the privileged administrators, they're the ones that can do things like deletion and disablement and changing policies. But all the other users in the other accounts, all they can do is make use of those keys with encrypt and decrypt. And then, of course, if you want to dig into deeper on all those compliance reports and understand how KMS is in scope, read more about the controls we have inside the SOC, you can go to AWS Artifact, which is available to every AWS account holder, and actually download those reports. And I'm super pleased to say that this is actually not an exhaustive list. There are more crypto-related talks here at Reinforce. Many of which will go into quite a bit of depth about how you use KMS, how you use Cloud HSM. We had a talk from one of our senior principal engineers earlier about network security and what we're doing in the area in crypto across the AWS network. The one at the bottom there, which is SEP 304, you can hear about our chief cryptographer talking about what AWS is doing in the area of quantum safe cryptography. So preparing for the emergence of quantum computing and the risk that that poses to public key cryptography. So whether you have a chance to see those sessions tomorrow or you go back in the YouTube catalog after the show, it's worth watching. Okay, that's it for my presentation. I will be outside the door there if anybody has any follow-up questions. Thanks a lot for your attention. Have a good show.